Welcome to the sixth session of our Nanoelectronics series of video lectures. In this session, we shall discuss about one effect that magnetic field can produce in nanostructures, that is the Aharonov-Bohm effect. So basically, we have seen that when magnetic field act on crystals, it may collapse the energy level of those electrons, or it may cause oscillations in those devices. Now, let us see what does Aharonov-Bohm effect generate. Basically, the magnetic fields can produce and control the interference effects between electrons in the solids. So, if you want to observe these interference effect between the various electron waves, we must ensure that these electron waves have their phase maintained, which means any two electron waves must have a constant phase. The phase of these electrons must not change. But if the electrons are moving inelastically or they interact inelastically with other defects in the system, their phase may get destroyed. So magnetic fields can produce interference effect. So if you want to observe the interference effect, you want to preserve the phase. But in most cases, the electrons may destroy their phase due to their inelastic collisions. Thus, only ballistic electrons whose mean free path is greater than the dimension of the device, capital L, they can travel through the lattice without scattering, and these ballistic electrons can show interference effect. Our requirement is to generate ballistic electrons so that we can observe the interference effect that this magnetic field produces. So this is the essence of the Aharonov-Bohm effect. So what was this effect? It was in 1959 that two scientists, Aharonov and Bohm, proposed that an electron wave in a solid has a phase which can be controlled by a magnetic field. So they just propose that in whatever be the solid, the electron waves has a phase which can be controlled by a magnetic field. Later in 1985, the scientist Webb at IBM tried to prove this theorem. So what he did was, he took a metallic ring of diameter 800 nanometer. It was made of wire which had a thickness of about 50 nanometer. So we can see this, right? So this was our structure. So this through P we had the inlet and Q was the outlet. Now the electrons entered this ring from the point P, and at P the electrons split, the amplitude of the electrons split equally. So we have a path, and from there is a diversion. We have two paths, say path 1 and path 2. So to both the paths, this electron amplitude split equally. And finally, these both electrons are traveling along this path, and finally they meet at the point Q. And when they meet at the point Q, there may be an interference, or both these particles electrons are interacting, right? So there is a great chance of generating an interference. Now suppose what I am doing is I am creating a magnetic flux. I am creating a magnetic flux in this region, inside this ring, which maybe perhaps by introducing some solenoid. So solenoid, they generate magnetic flux, right? So let me introduce a solenoid into this ring, inside this ring. So what happens when a magnetic field comes across this structure? For an electron in our magnetic field, their momentum, we may replace their momentum P and equal to P plus E into A. This is what we discussed in the previous session. Here A is your, let me find it here. Here A is your vector potential, where B equal to curl A. Now as your electron moves from a point P to Q, there is a change in phase. So there is a two directions, right? So let the phase be initially V. So since the electrons split up, there definitely will be a change in phase once they reach Q. Let me represent this change in phase as by this equation. VR equal to E by H integral P to Q, inlet to outlet, A into ds. A is a vector potential related to a magnetic field by this equation. ds, what is that? Differential with respect to your surface. Now let me further change it. Delta V, the change in your phase, can be represented by V1 minus V2. Now what may be V1? The phase of this electron, and V2 is the phase of this electron. So this change in phase is being calculated. Once they reach the point Q, what is the change in phase? So you can write it as the same equation, right? I am changing this integral. So E by H integral of A ds in the lower arm minus the upper arm. Here V1 is the phase in the lower arm and V2 is the phase in the upper arm. Now let's see that. What is this? So lower arm and upper arm, which in fact constitutes a circle. So I change my equation as delta V, or the change in phase, is equal to E by H integral A ds over my circle, because this is nothing but the lower arm and the upper arm forming a circle. Now let me use my Stokes theorem here. Integral over a circle f dot dr equal to the surface integral curl f dot ds. So here instead of f I have a, dr is ds. So their equivalent value will be surface integral curl of a into ds. So let me rewrite this curl a into ds. This integral circle a dot ds is equivalent to integral curl a dot ds. I am using a substitution for this term as phi, from which I get delta V equal to E by H phi. Let me make this clear once again. You have this equation for change in phase. I am splitting this from P to Q. Since I have two directions, I am splitting it like this. The lower arm and the upper arm. The lower and the upper. Now they form a circle. So I am rearranging this equation in this form. Now from Stokes theorem we have integral over a circle f dot dr equal to the surface integral of curl f dot ds, since it's surface integral. This is line integral, right? So let me apply this. Here instead of f we have a, so the equivalent will be surface integral of curl a dot ds. Curl a dot ds. Let me represent this by phi. In that case, this is nothing but phi. So my equation changes delta V equal to E by H phi. I hope this is clear right now. Now, here let me represent this term E by H. it's nothing but a constant, right? So I'm giving a new variable phi naught equal to h by E, and I name this as the quantum of flux. And finally, you get the change in phase delta V equal to V1 minus V2. It's nothing but 2 pi phi by phi naught. Now why is that so? Phi naught is h by E, and here we have h bar. H bar is h by 2 pi. Let me use the pen. Here h bar is, here we have E by h bar, right? H bar is h by 2 pi into phi. Now this term is 1 by phi naught. So what do I get? 2 pi phi, this term, divided by phi naught. I hope that's clear. So this is the equation for your change in phase. So we can see that there is a complete oscillation when you change the value of phi by a quantum flux phi naught. And this variation in phase can be obtained when you change your magnetic field B, even if your electron is not directly subjected to B. So what has Aharonov-Bohm effect generated? They have generated they have generated oscillations. They have generated oscillation in a closed ring. So for that, what we did was we took a metallic ring. We introduced a magnetic field in this ring using a solenoid. So we saw that as the electron entered, there was a splitting of amplitude, and once they reached the end point, there was an interference. Now we are trying to find the phase difference in this. So to find the phase difference, we considered this condition, and from there we use this condition because our path of travel was through the lower arm as well as the upper arm, together forming a circle. Using the Stokes theorem and small simplification, we have obtained this phase, and from which we realize that due to this effect, there was complete uniform oscillation in our material, and the phase can be maintained so that there is proper interference. So in order to observe those interference, we have ensured that your phase is conserved. So that's it. I hope this session is clear. Any doubts? Please let me know. Thank you.